everyone, welcome to CS188 section 11, and today we'll be doing perceptrons and neural networks. So the first problem is on perceptrons and segues into neural networks. So we'd like to use a perceptron to train a classifier for data sets with two features per point and labels +1 or -1, and they give us the data here. So they say that our two perceptron weights have been initialized to W1 equals 2 and W2 equals -2. We have two weights because we have two features. So after processing the first point with the perceptron algorithm, what will be the updated values for each of these weights? So with the perceptron algorithm, we take our weights and we dot product them with the feature. So we do W1 F1 plus W2 F2. So this is 2 times -1 plus -2 times 2, and that equals -2. Since we're doing binary classification, if it's less than 0, then we label as -1. Now note that this is wrong, because our true label is actually 1. So, since it's wrong and the correct label is 1, we add the feature to the weight. So we do the update W1 equals W1 plus F1, so that equals 2 minus 1 equals 1, and we take W2 and we update it to be plus F2, so that equals -2 plus 2 equals 0. Now question 2, they ask after how many steps will the perceptron algorithm converge? Write never if it will never converge. And one step means processing one point, and all the points are processed in order and then repeated. So whenever they ask for convergence, convergence means that there exists a linear boundary in feature space. So let's draw a plot. So if we draw a plot, and we'll do the ones as pluses and the -1s as minuses, then we'll get a plot that looks something like this. We get a plus here, a minus here, a plus here, and a minus down here. So by looking at this, there's no single line in which all pluses are on one side and all minuses are on the other, which means that it'll never converge. Okay, so now they ask us, they say instead of using the standard perceptron algorithm, they want us to treat the perceptron as a single node neural network and update the weights using gradient descent on the loss function. And they say that the loss function for one data point is the guessed label y minus the true label y star squared. So given a general activation function g of z and its derivative g prime of z, what is the derivative of the loss function with respect to w1? So first, let's write out what the loss function is. So the loss function of y and y star, well, they already told us that it's y minus y star squared. But what is y? Well, y is our guess. So it's some function g of our dot product, w1 x1 plus w2 x2. Minus y star squared. So what is this activation function? Well, we'll actually get to that in the next part 4. So you can think of, we do this dot product, and then g is what we decide to do with it. Do we decide to label it as a -1 or a +1? Okay, so now that we have this, let's write out our loss function. So our loss function is going to be 2 times g of w1 x1 plus w2 x2 minus y star times the derivative, we're applying the chain rule, of g prime of the same arguments times the derivative of the arguments with respect to w1, which is going to be x1. Okay, so moving on to part 4, they tell us the activation function. And what they say that the activation function is this is a step function. So I can draw a little plot of what it looks like. So if we have z on the x-axis and g of z on the y-axis, it'll be something like this. So it's +1 when it's greater than 0, and it's -1 when it's less than 0. So this is what we actually did up here when we did this part. Okay, so we already did the gradient descent equation, and now what they're going to ask us is what are the updated weights after we do this. So what we're going to notice is that d loss with respect to dw1, this depends on the derivative of the activation function g prime of z. But let's look at it. What is the slope at any point? Well, g prime of z always equals 0. It's always a horizontal line, ignoring the corner case, which happens as z equals 0. So if g prime equals 0, this also means that because we're doing the chain rule and we're multiplying them all together, this means that the derivative of the loss with respect to g1 equals 0. Now what does this mean? That the weights don't change when we do the update. Okay, so what is the most critical problem with gradient descent with this activation function? Well, the main issue, we kind of just talked about it, is the gradients are always 0, which means that the weights never change. So basically the algorithm does nothing. So this kind of shows that the loss function matters a lot and the activation function matters a lot. We need to be able to get gradients. Okay, so let's move on to part 2, which is on purely neural nets. And we're considering the neural network below with 2 neurons for binary classification, where x, the input, is a real value, and we're trying to learn a class y equals 0, y equals 1, and the unknowns of these weights, w1 and w2, and we have some activation functions. They don't really tell us what they are, g1 and g2, and the output is a2, which is between 0 and 1. And they also will give us a loss function. If you need a reminder, look at the overview lecture before this. So in part A, they say let Z1 and Z2 refer to the pre-activation. So Z1 would be right here and Z2 would be right here. And now they want us to write them in a chain. So we can say that Z1 equals W1 times X, and then A1 is we take G1 and we apply it to Z1, and then Z2 equals multiplying W2 by A1, then A2 is applying G2 to Z2. And again, I'm doing some of this work will have overlap with the overview lecture. Okay, so now they want us to write the output A2 in terms of x, the weights, and the activation functions. So basically they want us to collapse part A into one single equation. So from A2, that's what we want. We'll start at the beginning. We start at x, multiply by W1, push it through the function G1, then multiply by W2, then push it through the function G2. Okay, now they want us to use the chain rule to derive d loss dw2. So we went over this exact example in the overview lecture. So what we do is we work backwards. So we start with the loss, so d loss, and now what is the loss in terms of? Well, the loss is in terms of A2, so we have dA2. Now we put it on top because that's what the chain rule does. Now what is A2 defined in terms of? Well, it's defined in terms of Z2. Now we put that on top according to the chain rule. Now what is Z2 defined in terms of? Well, it's defined in terms of W2. Now if you do dimensional analysis, the A2's cancel, the Z2's cancel, so on the right side we really do get D loss dW2. Now in part D, they're going to have us do the same thing, but for D1. So we're going to start out the exact same. What is the loss in terms of? It's in terms of dA2. Now what is dA2 in terms of? It's in terms of Z2. Now what is Z2 in terms of? Now last time we put W2 because that's what we wanted. But since we're moving back through the neural net, we're going this way, we want to keep going until we get to W1. So we're going to actually go with dA1 since that keeps going back to the neural net. Now we take dA1, and what is dA1 in terms of? In terms of dZ1. And what is dZ1 in terms of? Well, finally, it's in terms of dW1. Okay, so now we have applied the chain rule for both W1 and W2. And now in part E, it says, okay, here's a loss function. It's going to be the squared error. And they're going to tell us that G1 and G2 are sigmoids, with 1 over 1 plus e to the negative z is the equation. And they also tell us this convenient fact that the derivative of the sigmoid is this quantity right here. Now they want us to write the terms here, the derivatives, in terms of the intermediate values, and the current weights, and the current inputs in the label. So x, y, w, a, and z, which we all know because we start with the input x, and given our current weights w1 and w2, we fill in all these values. We fill in what part A gave us. So we have all these intermediate values. Now we need to calculate these. So let's do the shorter one first. So d loss dw2. So if we look above, what's d loss dA2? Well, that's going to be minus 2 times y minus a2. Now, what's the derivative of a2 with respect to z2? So we look here, and it's going to be the derivative of g with respect to z, and they give us right here. So that's going to be g2 z2 times 1 minus g2 of z2. And the last term is derivative of z2 with respect to w2. So if we look up here, we see that that's going to give us a1. Now we can write this out a little bit more and fill in the value for G2 because it's a sigmoid. So I'm going to get 1 over 1 plus e to the minus z 2, and 1 minus 1 over 1 plus e to the minus c2, a1. Okay, so now we can do the same exact thing for d loss dw1. So we know that the first two terms are going to be the same. So d loss dA2, and now dA2 dZ2 is the same thing as we did for W2. Now we get dZ2 dA1. We look up at our equations, and dZ2 dA1 is W2. Now we get dA1 dZ1, so that's going to be similar to before. It's going to be G1 prime of Z1. So if we're using this again, it's going to be G1 of Z1 times 1 minus G1 of Z1. And the last term is dZ1 dW1. So we look up at our equations in part A. dZ1 dW1 is just x. So we could fill these in. So this is, remember that G2 is a sigmoid and G1 is a sigmoid, and we have that value right there. So we're able to calculate both dloss dw2 and dloss dw1. Now in part F, they want us to write the gradient descent update for w1 in terms of step size alpha and the values computed above. So the gradient descent update is w1, and it's going to be, we want to go in the opposite direction of the gradient, so negative gradient, and the step size is alpha. And dloss dw1, we already calculated, is here, and you would plug in that value.